Okay, yesterday our focus was on vertical asymptotes, and today we're going to focus on the horizontal asymptotes. And horizontal asymptotes and end behavior are really the same thing. So if you can think back to pre-calculus, how did you find end behavior of rational functions? Mostly is where we run into this in pre-calc. Do you remember that there were 3 rules to find end behavior or horizontal asymptotes from pre-calc? They had to do with like degree of numerator, degree of denominator, and all of those things. And personally, I forget those all the time until I review them with a class that I'm teaching, whatever that happens to be. So I don't use that method very often just because I do forget them all the time. So maybe there's a better way where we don't just have to memorize rules. Maybe we could just use analysis of functions or calculus to determine horizontal asymptotes. So horizontal asymptotes are going to be what happens at the quote-unquote end of functions. So are they leveling off? Are they going to infinity or negative infinity as x goes to infinity or negative infinity? That's how we find horizontal asymptotes. So this f of x function, if you remember the rules from pre-calc, you would know that the horizontal asymptote is y equals 3. Again, just like vertical asymptotes, horizontal asymptotes have to be equations, and they're horizontal, so they have to be y equals. So this horizontal asymptote is y equals 3. Here's the graph of that function. Okay, we can see that they have the asymptote drawn in, and the function there is drawn in black. And you can see that the limit of our function, as we approach negative infinity or positive infinity, we're getting really, really close to that horizontal asymptote. And that's how we use calculus to find end behavior or horizontal asymptotes, if there are any. Okay, so if we had just evaluated limit as x approaches infinity of that function, or limit as x approaches negative infinity of that function, we would have gotten both of these to be 3, algebraically speaking, as well. So the line y equals L is a horizontal asymptote of the graph when, exactly what we just said, you take the limit as x approaches negative infinity and positive, and you should actually check that out, both directions, because there are very strange functions, and we'll see one, where the limits are different based on whether you're going to positive infinity or negative infinity. It doesn't happen often, but this is calculus, so every once in a while it pops up. Limits as we go to infinity have the same properties as we had discussed in the previous sections. So for instance, if you're taking the limit of 2 functions added together, you can add their individual limits. If you're multiplying, you can multiply their individual limits. Those things still hold for x approaching infinity or negative infinity. Then there's this little thing down here that talks about if we have the limit as x approaches infinity or negative infinity, if it's defined, c divided by x to the r. So really big numbers to a power are going to just get gigantic in the denominator, and we know that a constant c divided by really big numbers is going to be very, very small, so we say those limits are 0. And that's just a theorem, so you can use it at any point in time. This is considered common knowledge once we talk about the theorem. So let's look at this. First example here, limit as x approaches infinity of 5 minus 2 over x squared. So our property from before that still holds, says we could take the limit as x approaches infinity of 5 and subtract the limit as x approaches infinity of 2 over x squared. Now that second limit there, the 2 over x to a power r, is that last box we just talked about down here. This is what we're talking about. We know that limit goes to 0, so check out this weird notation. You can just kind of cross it out with an arrow saying that goes to 0. Now we know you have evaluated that. And then the limit of 5 as x goes to infinity, that's just a constant. So we say that this limit is equal to 5. Okay. One slightly harder than that, with a little hint or a pro tip up there, divide numerator and denominator by the largest degree term of the denominator. The textbook, if you look this stuff up in your textbook, has a little bit different process, which is fine. I just do it differently. So largest degree term of the denominator when you have rational functions is how I like to evaluate these. So our largest degree term is x to the first. So I'm going to divide everything by x to the first before I can evaluate. So 2x over x is 2 minus 1 over x all over 1 plus 1 over x. Okay, now what that allows me to do is use that same trick I did over on the left-hand side, where any constant over an x going to infinity goes to 0. So at this point, my 1 over x goes to 0, both on top and on the bottom, and I end up with a limit of 2 over 1, or 2. Okay, and it's super fast because I divided by the highest degree term of the denominator. Let's do some more. This is an example of one of those really strange things where I am actually going to divide by what's going to look like an x, but in the denominator, my highest degree term is an x squared, but it's under a radical, and the square root of x squared, is either plus or minus x. So square root of x squared is either a positive or a negative x, depending on whether we're going to positive infinity in this first one or negative infinity on the second one. So let's see how this works. The first one, I'm going to divide by the square root of x squared on top and bottom, which, because we're going to positive infinity, will be positive x. So let's see what that looks like. And you write it differently in each spot. So if I do 3x divided by a positive x, I get 3 minus 2 over x. And in the denominator, it's under a radical, so I'm going to do 2 plus 1 over x squared. Because I'm dividing by square root of x squared and positive x. All right. So I evaluate, same way we have been doing. 2 over x becomes 0, 1 over x squared becomes 0, and I have a limit that equals positive 3 on top and a square root 2 on the bottom. And I'm totally fine with radicals on the bottom, remember. All right. Fun. Now, same function, but we're going to negative infinity. So this time, we're going to think of that as a negative x when we divide on top. So let's see what that looks like. See if we get the same thing. So limit x approaches negative infinity, and 3x divided by negative x is a negative 3 plus 2 over x squared, because two negatives make a positive. And denominator, because it's going to be x squared, it's going to look the same, 2 plus 1 over x squared. Okay, we use our magical little trick. That one goes to 0, that one goes to 0, and we get negative 3 over square root 2. Okay, so this function, our 3x minus 2 over the square root of 2x squared plus 1, has two different horizontal asymptotes. What a weird function. If you want to see what that looks like, I would suggest graphing it on your graphing calculator. And you will see that it's a little bit crazy, but it does indeed have two different horizontal asymptotes. it happens to be a function that kind of does one of these things. Okay, so it has a horizontal asymptote down here, and it has a horizontal asymptote up here, which you can see by graphing. Okay, let's evaluate some more limits as we go to infinity. So if we can get a value, it's a horizontal asymptote. If it increases or decreases without bound, then we would have just end behavior, which tells us some important stuff as well. So if we're doing this first one, in the upper left-hand corner, x approaches infinity of x cubed. If we have infinity cubed, we're just going to get bigger infinities. So we say that one equals infinity. And I want you to write equals infinity instead of does not exist again. Okay, let's jump over to the right-hand side here. X approaches negative infinity of x cubed minus 2x minus 7. So we would end up with a negative infinity cubed minus 2 times negative infinity minus 7, if we're thinking kind of along the lines of direct substitution, even though infinity is not really a number. This is going to be a negative infinity. This will be a positive infinity, and that will be 7. Now, a lot of people think that if I add negative infinity and positive infinity, that I'm going to get 0, but that's not true. One of those infinities is much larger, much farther away from 0 than the other. If I cube infinity, that's going to be much farther away than just multiplying by 2. So because this term is going to win, it's bigger than all of the rest of them, we say this limit actually equals negative infinity. Okay, the next one, a little bit more challenging to figure out. We have a rational function again, and you can use the pro tip where we divide by the highest degree term of the denominator. So this is going to be limit x goes to infinity, so we're dividing by x squared. X over x squared is 1 over x, plus 1 over x squared, 2, plus 2 over x, plus 1 over x squared. Okay, and that simple little trick really just gets rid of a whole bunch of stuff for us. Those were arrows. All of those go to 0. So what did we end up with in the end? We have a 0 over 2, and 0 over 2 tells us that limit is 0. So that has a horizontal asymptote of 0, which maybe if you remember the rules from pre-calc, you already knew that. Next one, last one, before you can work on your assignment, we have thinking about e to the infinity power minus 3. E to the x, because e is bigger than 1, it's not a fraction, it's larger than 1, it's an exponential growth. No matter what power we raise it to as we're going to positive infinity, this just gets bigger and bigger. Subtracting 3 really has no bearing on it, so we say that is equal to infinity as well. Okay, hopefully that helps you out figuring out end behavior and horizontal asymptotes. If you have any questions,